Okay, so for this paper, for the speakers, James Day, he got his PhD at Birmingham University, working with Graham Pearson. So for Graham Pearson, for any people working in mental geochemistry, should read his publications as Treatise Geochemistry in 2003 and 2014. So he's a quite a good expert in the mental geochemistry community. So James Day worked with him, and then he moved to University of Tennessee for his first postdoc, and then at University of Maryland, working with Rich Walker for his second postdoc. First postdoc he worked with what's his name? Larry, I forgot his full name. But both of his postdoctoral advisors, they work on the different types of lunar samples, and they use the mass spec to mainly focus on the elemental and isotopic ratios of this highly siderophile elements. So like rhenium, osmium system they work on, and then you have the platinum, palladium, ruthenium, etc. So for these elements that people measure them and look at the isotopes too. So for the story of using these elements to trace the Earth process, it lies in at the very beginning of the some simple observations. So the first line of evidence is coming from experiments. So what people looks at that is that the partitioning, which the partitioning coefficient of I between the metal and the silicate is extremely high. So it's in the order of 10 to the order 4 to the 10 to the order 7. So that means when people get a meteorite, to assume that is close to the bulk composition of the Earth before the Earth core mantle fractionation. So if suppose we have 1 ppm of an element, for example, for palladium actually is not too bad assumption. In the bulk Earth, for example, and what you are going to get is that with this partitioning coefficient extremely high, that means almost all the palladium are going to go to the core. So leaving the metal extremely depleted in that. So that means in a mantle, if we just do this calculation, and let's use 10 to the order of 5. So that means in the mantle, you should only have this amount of palladium in the mantle or in the bulk silicate Earth. And then in the core, then basically you should have all this 1 ppm. I said palladium going to the core. So we could do more detailed mass balance calculation, but in general, if you look at the orders of magnitude, it's something like that. That means almost all of the highly hydrophile elements going to the core, and very few should leave in the bulk silicate Earth. So that's what the people measured, and then the evidence come from natural samples. So that's the first experience. The second is from Apollo mission. So you know that the people that went to the moon. So 1969, Armstrong got on the moon. 1972, that was last time human got on the moon. So brought a couple of samples back. So through that process, people get more lunar samples, but it's also at the same time that people began to develop a mass spectrometer that could measure the lunar samples. But people use the exactly same method to look at the Earth samples. Then people use this developed measurement, and that's what Cho had said, etc. In 1978, and he's at the University of Toronto. So what he measured is that he looked at the upper mantle samples, mainly the upper samples, basalt stenoliths. So he measured the highly siderophile elements like palladium, rhenium, like the palladium, ruthenium, etc. So he measured these elements and they find that these elements are not too low. So they're in the order of like the ppb level, like several ppb, maybe like a 4 or 5 ppb level, something like that. Not of all, let's say for palladium, for example. So because at our calculation, if we know the bulk Earth composition, look at the partition coefficient, then what lies in the Earth's mantle should not be at a ppb level Padium, should it be in order like a ppt. So not even ppb, but the ppt level should be more reasonable. So, but in the end, that we have too much of this highly hydrophile elements in Earth's mantle. So then he claimed that not he, but other people also claim, okay, during Earth's formation process, accretion process, we have lots of components added later on. So for those lately accreted components, they basically coming from the bulk composition of the planet, not necessarily to the Earth, but maybe to some other, like say, chondrites that we have. So for those chondrites, you could consider they have a core, they have metallic core. Maybe they are differentiated, maybe not. But in the end, they come with something that could be equivalent to a certain extent to the bulk Earth composition. So basically, you end up with a mantle, or with a beginning, with a core and with a mantle. After differentiation, the mantle is extremely depleted, and you have some further components added to the core. So you could consider this further components as a bulk Earth or some other volatile rich chondrites. But for this added components, they have much higher concentration because they haven't differentiated the mantle of the core. So you add some components, and according to Cho's calculation, it needs about like 2% of this component so that you can match the observation of this ppb level of this highly hydrophile elements. So that's what Cho did in 1938. And then is until like at the time of, let's say, Harry Becker in 2006. So he's at the Berlin Freedom University. Actually, he's a PhD advisor of Zaicong Ma, or Wang Zaicong, who is one of our collaborators for calcium isotopes. So in 2006, what Becker did was that, okay, he measured this upper mantle samples as well as the meteorite samples in much more detail than what the people used to measure. So he improved his analytical resolution. So what he got was that, okay, he found that not only we have this palladium, radium, osmium, ruthenium, etc. Also, he found that for if we use iridium as a standard, then ruthenium as well as palladium, iridium of these two ratios are much higher than the chondrites. So high. So larger than chondrites. So what does that mean is that, okay, we have a core, we have a mantle, then you think we add some later components, but so you have a chondrite added to the mantle to match the concentration, but you cannot explain this ratio because you add a chondrite, then you should have a chondrite ratio of a ruthenium, palladium, iridium, right? So you should not have this, let's say, bulk silicate earth ratio that's significantly higher than that of chondrites. So that has become a problem. And later on, that people also measured some other elements and look at, let's say, lead, sulfur, as well as some other ratios that people find is really weird. So there's a possibility people propose later on. So for example, one possibility is that, for example, you could add a chondrite, for example, that is already differentiated. So you have add something that has a core, have a mantle, and then the core directly goes into the core, and the mantle did not. So then you could help a little bit with this process for this mass balance. So, hi Arka, could you hear us? Hi Arka, I'm doing some explanation for this paper, and later on you could continue with the presentation. And so this one way, another way that people propose is that, okay, in a mantle, I won't go into details. So in the mantle crystallization, there are some hydrogen meth, basically sulfide that precipitated from the mantle. So because for sulfide silicate and the metal silicate. So metal silicate basically is iron silicate at the mantle core, and sulfur silicate are some, let's say, later components, hydrogen components in earth mantle. Because for iron, sulfide. Okay, because the element partition coefficient are different between sulfide and silicate, and also different than iron and silicate, and therefore that could explain this different ratio. So that's one way to explain it. So that people are still working on it. It's an ongoing process, not done yet. But Becker did propose something that's really good. Then is the author of this paper, James Day, came in 2007. So what he did was that, okay, he measured some moon samples from Apollo mission, which is called the box silicon moon. And what he got was that, okay, he found that this moon samples has extremely low highly hydrophile elements concentration. So for pallium, platinum, rhodium, it's much, much lower. So it's equivalent to 41, less than 40% of the BSE concentration. So it's extremely low. So that's what James Day found at that time. But when he found it, then he also mentioned about that why this concentration are too low. Because this later accretion process that you added some more contrast is not only the way that we look at these concentrations, because there's some other process that's relevant. So what is other process relevant? That's also relevant to the sulfide silicate process. Because in the Earth, if you look at the MORPH, mid-ocean rich basalt, for example, so if you look at the MORPH source, MORPH, then when there's a partial melting occurs here, the beginning of the partial melting, let me see, this is a partial melting. Then if you have very low degrees of partial melting, like 1%, like 10%, 20%, if you have very low degrees of partial melting, you will come out with a silicate melt that doesn't carry too much sulfur. And for the bulk system, they leave the sulfides behind. And because you have some sulfides behind, and sulfides has a density about 30 to 50% higher than silicates. So those sulfides, they just stay in the source. And then your elemental partitioning are going to determine by these two phases. So for this system, sulfide still strongly favors palladium, platinum, rhodium, rhenium, osmium, let's say, etc. So the whole idea is that, okay, as long as you have sulfide, you have that. But when you get higher partial melting extent, for example, 10% or 20%, something like this, then your silicon melt dissolve all the sulfides because they're only like 0.01% of sulfide in the metal source. So all the sulfur is dissolved in the silicon melt. And then this system will determine the silicon melt and olivine, pyroxene, garnet, or spinel. So basically this partition system will be changed. So because there are no sulfides available, sulfides are more being consumed. So people have an argument because when you collect one sample at the surface from the Earth or from other planets, there are two things we need to consider about. So one thing is at the source, how it looks like. So at the MORPH source, at least as we know, is that you have to consider the sulfide silicate equilibrium. And then until the sulfide being exhausted. And at the surface, you have to consider two processes. So at the surface, what you need to consider is that you have the magma. Then the magma will cool down. For example, at the basalt, you have 1300 degrees C basalt coming there, then they are going to form into some new crystals, right? So these new crystals will also fractionate this highly hydrophile elements. So for example, there are metals and sulfides formed during the crystallization process in the cooling at the surface. And then these phases were highly enriched in these elements. So actually for the paper that Arca is going to present, they measure a lot of this metal sulfide. So this is one thing when you consider in the cooling. And second thing that we need to consider actually is the contamination. Is that, okay, you sample at the surface, then you may have some sediments. For example, on Earth, they consider sediments. And then on the moon is regolith, right? So those are some compact components that are hidden in the moon and living on the surface. But those compact components are enriched in highly hydrophile elements because you can consider they are contrast, different kind of contrast composition. Hidden moon are left on the surface of the moon, and they could be as thick as 1 to 3 kilometers, as this paper claim. So you have to consider. So you have these two processes that you need to consider when you get the final composition of the samples you get. Oh, I forgot calling one thing. Is that you go to this page. That is the morph looks like. Is that in a morph source, we think that it has a sulfide to begin with, and then it is being exhausted. But on the moon, what the people think that at the beginning, for the day 2008-7 paper, they considered that there was no sulfide because the moon is extremely depleted in sulfur. So they, from this argument, all those moon samples in this mantle source, when it is being melted for those mere lunar basalts, they just don't contain any sulfides to begin with. So you don't need to consider sulfide silicate partitioning process. But for Brennan, 2019 Nature Geoscience paper, which I attached to the email, and Brennan argued that in a source, the sulfide should be considered because although on the moon, the sulfur content is low, about 100 ppm or less, but the sulfur's solubility in the silicate melt of the moon is extremely low because the oxygen fuel gas is low. So that's Brennan's argument. So you still have a source that becomes sulfide saturated, and therefore most of these elements, highly saturated elements, resides in the sulfide in a lunar source. And what you get at the surface samples, the fresh sample from the lunar mantle, are highly saturated elements depleted. So what do you see for the lunar samples with this relatively low components could be a mixture with some of the regolith at the lunar moon's lunar surface. So that's Brennan's argument. So that's why that James Day is still debating with Brennan for this, and he's going to use some more evidence as what he's showing in this paper to say that the surface regolith and the lunar mantle sample mixture could not lead to the concentrations we see. From my perspective, my interpretation, that's the most important argument he's trying to get. And then he's going to present more detail. So yeah, so that's about this. And I'm going to forward this slides to you later on. And so with that, I'm going to stop sharing my slides, and I'm going to let Arca to share the slides. So Arca, please go ahead.
Okay, I'll just share my screen. Is the presentation visible and am I audible?
Yeah, it's good. Go ahead.
So I guess today is the first paper presentation that we are doing in this year. So I would just wish a happy new year to everyone and get started with this paper. I think Dr. Zhang has talked a lot about the paper already. And so this is the author. He presently works at the Scripps Institute in the States. Uh, he leads a lab over there, the isotope biochemistry lab over there. There is research interests on isotope biochemistry, cosmochemistry. He is a lot interested in planetary geodynamics and geology. Moving on to the keynotes of the paper, the paper studies about the high siderophile element concentration, and presently what Dr. Zhang actually ended with, that was, I think that is the question that he tries to answer, that how the sulfide and metal content, how did it, like, why the abundances are there. So it can help us to lay a insight into the constraints on accretion and differentiation. And with the with, if we see the cobalt nickel ratios, as it will be dealt later in this presentation, the accretion of a core is highly likely. The compositions of metals and sulfides in mere basalts are inconsistent with the assimilation of impact. This was also said by Dr. Zana as I was listening in the later part of the meeting I joined. And the assimilation, the models that are predicted by previous researchers, they don't actually stand a point. There are around 5 points that the authors have given that assimilation impact leading to a high HAC abundance is not really feasible. So with that, on the screen on the left hand side is a normalized ratio, the graph that we see. And on the right hand side, we see the concentrations of the sulfides and the metals and on the host element. So if we see that elements bearing nickel, elements bearing cobalt, from nickel to iridium, osmium, most of them actually concentrate in the sulfide and the metals. So, however, also we see at the red circle over here, a consistent amount of iridium, and they also reside in the chromium spinel part. So if we see at the chondritic, carbonaceous chondritic normalized values, we see that palladium shows certain differences over here. Just a minute. So the thing is that in order to get the metals, like metal and sulfide in mere basalts, because if we see that the terrestrial basalts are essentially metal free. So in order to get metal grains, what indicates is a reducing condition we need. And this might have occurred because of the iron liquid segregation at high temperatures or reduction during crystallization. This is what has been suggested previously. So the sulfide grains in mere basalts can form in form of localized crystallization in spinel or iron-rich silicates. This model actually explains the stability in low FO2. What it explains is that iron-rich silicate phases that endanger metal and sulfide stability in low oxidation FO2 condition melt. So if we see that cobalt is actually, or CO is actually associated with Fe-rich pyroxene and olivine. However, what the resultant low nickel cobalt actually happens due to a due to a metal saturation interplay in between them. And on the right hand side, what I just said, that metal and sulfide grains, they are the major host of the HAC metals, that high siderophile elements in the metal. So we see that there is a dominance of metal and trialite in the HAC budget of mere basalts. We basically, what we can see is that in the next slide, if I go, that there is a relative range of the absolute and relative abundances of this HAC in the mere basalts. Now, if we see that a high magnesium content which actually relates to a weak fractionation, has a relatively flat normal chondrite normalized bulk rock HAC pattern, whereas a low MgO content has a total lower HAC. Now, what we can along with this, what we can lay an insight is to is that the metal and sulfide data, if we show that there is a possible removal of a minor fraction of this metal and sulfide phases, this leads to a more pronounced palladium platinum ratio and less pronounced iridium osmium fractionation, such that the low magnesium content mere basalt rocks, they require less than 0. Around what they have stated is less than 0.1% of chlorite and metal removal during fractionation of the parental melts. On the graph on this side, we see that what they did a modal recombination. So the red lines, they show the bulk rock basalts. On the other hand, when they did a modal recombination along that is shown along the black line, they were able to match the mere basalt bulk rock compositions very well. So it matched very well with the sample specifically named 15555, and where all the major mineral phases that were measured matched with the modal recombination, and almost matched the HAC content. So the bulk rod data for certain minerals were a bit higher for certain samples, and certain phases were a bit higher. However, the modal recombinations, collectively the interpretation of this work was that the new mineral HAC and siderophile data demonstrate the major control of sulfide and metal during basalt crystallization process. So the following section we'll see that how the assimilation contamination has been disregarded, but what majorly is shown over here, that if we think of the MgO content and if we think of the fractional crystallization, that fights or explains the mineral the HAC abundance. So this is a graph over here. There are a set of few graphs over here. What they see that the circumstantial evidence is shown by previous workers that there will be regolith contamination. However, so one of the works of Burnham showed that the melting of whether the assimilation of impact contaminated regolith materials would be responsible for HAC abundances or not was shown by Burnham in 2019. So he basically used near sulfur solubility and sulfide silicate partitioning data. In the models, he showed that the sulfide was exhausted as a residual phase around 7% of melting. So like the model used as the parental, so like Burnham et al., a 3% partial melt product model was used as the parental melt of the two of the source compositions and reported by them. So what was interpreted is that the mixing curves that we have shown in this, that is shown in this figure, represent evidence for the generation of primitive mere basalt melts that was subsequently contaminated by less than 1% of the regolith, experiencing the highest degree of fractionation. Also, there was so this suggests that any contaminations are likely to occur close to the lunar surface where fractional crystallization took place, in some mere basalt lava flows or something like that. However, if the orders of magnitude differences in HAC abundances of basalts and the relative chondrites normalized values led to the conclusion that actually such contaminations are happening. But one of the notable differences that we should see that in this figure 5a, that the total quantity of iridium, which is around 50 ppt within the mere basalts of MgO content of or 10% or greater, this feature is difficult to explain by regolith contamination. The contamination of basalts by this regolith material. So, for example, if an assimilation of 3% regolith with appropriate characteristics were inferred, it would lead to a far what is that if a regolith contamination occurred, uh, the degree of what to say anomaly would have been higher in case of iridium, uh, or as shown in the or like which is around five times of the shown model. If we see a full range of palladium iridium versus iridium as shown in D, part D of this figure, the this is also not constrained with the fact that if regolith contamination of this basalts happened, regardless the degree of like fractional crystallization, such a relationship can't exist. So, but the models do not predict the low Ru versus IR or the palladium versus iridium practically. So, as in figure F, this suggests that this regolith contamination was just a second. Consequently, what shows that so the range of this contamination shown by the previous models was very constricted. So if contamination was supposed to happen, it would have happened on a larger scale. So this is one of the theories, and then what they have dealt with was they showed that the cobalt nickel, the hafnium tungsten ratios, this ratios practically point towards a core formation, which would have facilitated the crystallization model they have suggested in order to get the silicate and the metal concentration or the high siderophile element concentration as shown. So this was pretty much about the paper, and honestly, not that much acquainted with the lunar models and this kind of studies. So I don't think that I did a very good job while explaining, but this is what I could. This was my takeaway from this paper. So I think that.
Okay.
No.
Okay. Thank you, Arka. So any questions from participants for this paper or for the relevant question? Any questions? So how's your school going, Arka?
Presently, I should I stop sharing the screen?
Oh, it's okay. It's okay.
So presently, my final semester is going on. So, like it's just started from yesterday. So let's see the previous semester. So we are going to have the offline classes. Let's see how it goes. Like almost after 2 years, we are going to have our offline classes.
Okay. So may I know that when does the semester ends in most universities in India? So when normally is the longest time of break for students in India?
Since we're running, for us, it will probably end around in this is February, March, April end, May beginning. It will we'll all be done with our exams and everything. I believe it is around May that the seasons end for most of the schools in India.
In May. Okay.
Yeah, April
Uh,
and May. That is.
Okay, and then the new semester will begin at June.
So the fresh semesters, like if I go for the first years of undergraduate or first years of postgraduate, they begin a bit late, like July end to August. But the regular semester, like for a continuing student, it will start very much at end of May or June beginning.
Okay, I see. Okay. So normally when does the JAM exam begin? The exam for IIT.
Exam for
The JAM exam.
the JAM exam.
Yeah, JAM.
Oh, the JAM exam that takes place. I don't know this year, like February, March, it does take place. So the JAM exam, our time it took place in like when the JAM you can give after you are like when you complete your bachelor sports, you can give the JAM exam. So we gave it sometime in early March, I believe.
Okay. Okay. I think that's so much about it for our first paper reading. And for next week, actually for both Sunny Hall and Adrian Lee is a little busy, so we won't read the paper. After all, next week is more like general talk of how data science applies in our geoscience community. So we could by going through the papers ourselves, just look at how it goes, and then we will talk to look at the speaker to introduce his involvement in the geology-related research. Actually, a lot of examples are coming from paleontology, but that's okay. We can learn a bit from that, and then we will continue with the schedule. So we're going to have a reading as 2 weeks from now. Okay, so on Wednesday we're going to see the speaker to give a talk, and I hope that everyone enjoy a good day, and for our good semester, and also for Humi to end your official schedule at the university. Although I think that you already go over time as your payment of your scholarship by Provide University. So basically now you don't accept any pay, right? Yeah, I hope that you finish the unpaid period sooner, but that's okay. Okay. Have a good day, everyone, and see you on Wednesday to the seminar. Bye bye.